Okay, in this video we're going to talk a little bit about a common reaction of carboxylic acid derivatives, like this acid chloride that we have shown here. That reaction is known as nucleophilic acyl substitution. Nucleophilic because there is a nucleophile involved, acyl because there is an acyl group, and then substitution because we are substituting out a leaving group and substituting in nucleophile. So we're substituting something for something else. Now let's take a look at the mechanism. This is actually much more simple than you might think. Apologies for my crappy looking benzene ring. I'm just going to draw out our acid chloride. Okay, so here we have our acid chloride. And here is our nucleophile, our OCH3-, so I'll draw that out here. I want to see if you guys can follow exactly how this sort of reaction differs to what we've seen before with carbonyls like this. The one thing that we've definitely seen before is that all carbonyl molecules will undergo addition reactions. And at first glance that's what this looks like. The nucleophile adds in to the carbonyl carbon and kicks those electrons up onto the oxygen. That should not be any sort of a surprise. We have a strong nucleophile, negatively charged, so there's no catalyst needed. It attacks at the most electrophilic site, which is that carbon. So if I draw out our intermediate here, we are going to see where this mechanism and thus this entire reaction differs from what you've seen before. Here is our O-, here is our Cl, and I'm just going to draw on the OCH3 as well. Okay. Now what we've seen previously is that once this forms, this O- goes and protonates from some acid or something like that in a second separate step. Now obviously you can see we don't have that going on here. There's no 1-2 steps, there is no acid around. And the reason for that is because this O-, it actually always has two options of what it can do. One option is to go out and attack a hydrogen from somewhere. However, it'll do that only if it can't do the other option. And we haven't seen the other option yet, so we're just going to talk about it now. This O- has one bond. It's unhappy. It wants two. And this CO, this carbonyl group, is an extremely strong carbon-oxygen bond, and that makes the carbon very, very happy. So if that oxygen can reform that carbonyl group, it will. But what we've seen in the past is that doesn't happen because there's no leaving group that can kick off this carbon and then give the carbon here 4 bonds back, rather than having it be a Texas carbon. Well, can you guys see the difference here? Well, that difference is we actually do have a leaving group, and we have a great leaving group. So what happens here is the electrons come back down onto that carbon-oxygen bond, forming a sigma bond and making a double bond there, and kicking out this leaving group, and that's the difference. That leaving group we have never had before. So what we end up with is this. Alright, so here we go, here we go, here we go. We have reformed our carbonyl group. We have added on, or we have substituted in the OCH3. We've made ourselves an ester. And we have Cl-. So if you just ask yourself then, well, which is the stronger nucleophile? Is it this, or is it this? Well, from what you've seen before, Cl- is very, very stable, so it's very happy to exist just by itself. It's much less nucleophilic than this, and so that's why when this reaction occurs, this stops here. Acid chlorides are extremely reactive, simply because that chlorine is a very good leaving group and is very happy to come off and stay off. And so all the nucleophilic acyl substitutions that you'll see, at least with negatively charged nucleophiles like this, will look exactly like this mechanism. In fact, you could take out this OCH3 and replace it with anything. NH2-, X-, whatever. And the mechanism would be exactly the same. The mechanism is only slightly more complex when you have neutral nucleophiles. Okay, so let's just have a look at that. And we're going to use the same acid chloride, so let's draw that out. So here we have our acid chloride, like so. And except this time we are going to add NH3 to it. So NH3, because it's not negatively charged, it's not as strong the nucleophile, but this carbon here is very electrophilic. It has the electrons pulled away from it from the oxygen and from the chlorine, so this is a very reactive molecule. So the nucleophile is always going to attack that same carbon, kicks the electrons up onto the oxygen, and when we draw out the intermediate, what we get is, it's something very similar to what we saw before. We have our O-, we have our Cl, and this is where the only difference is. We started off with a neutral nucleophile, so the nitrogen already had 3 bonds. And now we have a nitrogen that's got 4 bonds, so it wants to lose 1. But before it does, we're going to get to our almost product. The O- does what it did before, it kicks the electrons down here, kicks out that leaving group. Remember, we haven't seen that before. That leaving group wants to come off, so it will. And so when I draw out this, what we have is our carbonyl group reformed. We've lost our chlorine. But right now we have 3 hydrogens on our nitrogen, and we still have that plus charge. So what do you think we have that can remove one of the hydrogens and thus the plus charge? Well, it's the Cl-. Or if you have water lying around, water could do it too. It doesn't need to be a strong base, that can go in here. Kick electrons back onto there, and then what we end up with is this. Here's our benzene ring, not drawn very well. Here's our carbonyl group. And so what functional group do we have here? Well, that is an amide. We've made, from an acid chloride, which is very reactive, an amide which is not reactive at all. Okay. So you can see this is exactly the same sort of mechanism. The only difference is this last deprotonation step that always has to occur for a neutral nucleophile. But if you were to ask yourself, well, how do I draw out the overall product? If Dr. P puts one of these questions on an exam or on a quiz or something that says something like this, here is my, based on my starter material, and I want to add in, say, water. I'm going to do exactly what I did with ammonia here. Weak nucleophile, because it's neutral. Weak nucleophile here, because it's also neutral. But look at the final product compared to what you originally added in. You have lost one of your hydrogens from your nitrogen when you go to the product. And with every neutral nucleophile, it's always the same way. So when I draw out this product, I'm going to put the nucleophile where the chloride was, but I'm going to take off one of the hydrogens. It's a nice little shortcut there, so you get a carboxylic acid. Right? The only thing you have to be careful of is if you have a neutral nucleophile that looks like this, CH3OH for example, and you just apply the rule that you did before, you lose one of the hydrogens. Well, notice we lose a hydrogen from the heteroatom, hydrogen from the nitrogen, hydrogen from the oxygen, and therefore we lose a hydrogen from the oxygen here as well. So what that means is when it's added in, our nucleophile would look like this. Alright? And that, in essence, is nucleophilic acyl substitutions with both negatively charged and neutral nucleophiles.